Hello everyone, I am Dr. Fawzul Atiq giving some series of lecture for the course Discrete Mathematics. So in the previous lecture, we have introduced what is a recurrence relation, how the solution work, and we also understand that we need to find the solution of a recurrence relation. So in today's lecture, we'll discuss how to find the solution of it. Now, as we discussed in the earlier lecture that we'll find the solution of linear homogeneous recurrence relation, right, with constant coefficient of degree k. Now, I am writing a linear homogeneous equation, a general form. An is equal to, I am writing it as C1 into a constant an minus 1 plus C2 times an minus 2. Now, this is a recurrence relation, linear. This is homogeneous, constant coefficient of degree what? Of degree 2, according to the definition. And here C1 and C2, both of them are constant. Now, we first initially we'll guess that, okay, we need to have a solution of it. So we guess that, okay, that an is equal to r to the power n is a solution. Suppose we assume that. Then what will happen? If this is a solution, then it should satisfy the recurrence relation. So I'll substitute this n equal to r to the power n in the given recurrence relation. What will happen then? Then it will imply that r to the power n is equal to c1 times it's r to the power n minus 2 c1 time an minus 1, that means r to the power n minus 1 plus c2 times r to the power n minus 2. Right? Now this equation I can simplify it because r to the power n, n minus 2 I can take it common. So I can divide by r to the power n minus 2. So this will become r square is equal to c1 into r plus c2. Then I can change it as r square minus c1 into r minus c2 is equal to 0. So I assume that an equal to r to the power n is a solution. And because this is a solution, it should satisfy the given recurrence relation. So I got this equation. And after simplifying this, I got a quadratic equation of r. Right? So a polynomial equation of r of degree 2. Why this degree 2? So this because I have the last term is 2. So because the recurrence relation is of degree 2, so therefore I got a quadratic polynomial equation of r. So if I can solve this one, I'll get that an equal to r to the power n is a solution. Right? I'll get a solution of it. Now, therefore, that whenever I have a recurrence relation of degree 2, I'll get a polynomial equation of degree 2. This equation we called it as a characteristic equation. Right? So how this r square minus c1r minus c2. So this equation is called a characteristic equation. If you can solve it, we'll get the value of r and we can get the solution of it. Right? Now, I have a theorem. I have a theorem. This theorem says that suppose that let c1 and c2 are real number and suppose that r square is minus c1r minus c2 equal to 0 has two distinct root. Now because it's a polynomial equation of degree 2 and it may have equal root, it may have distinct root. It may have no root also. But if it has two distinct root r1 and r2, then the sequence an is a solution of the recurrence relation an equal to this one, that is our general sequence, the recurrence relation of degree 2, if and only n equal to alpha 1 r1 power n plus alpha 2 r2 to the power n. I'll give some example, it will be very clear. So I have the recurrence relation an is equal to c1 an minus 1 plus c2 an minus 2. Right? From there I got the characteristic equation of it. What is the characteristic equation? Characteristic equation is r square minus c1r minus c2. So that means whatever is the power, that will be the power r square minus c1, like reduced power minus c1 into r minus c2 equal to 0. This is the characteristic equation. So if you solve it, you will get, because it's a quadratic equation, if you solve it, you will get two root. If the roots are distinct, r1 and r2, two different root if you get, then according to this theorem, we will say that an is equal to, the general solution is alpha 1 r1 to the power n plus alpha 2 r2 to the power n. Right? What is unknown here? R1 and R2 we already find out. But alpha 1 and alpha 2 are new term. But that we'll find it with the help of your initial value. Right? So this is the theory behind it. Now I will give some examples so that it will be very, very clear to you. Look at this problem. What is the solution of the given recurrence relation? Look at this. An is equal to an minus 1 plus 2 times an minus 2. Is it linear? Yes, linear. Homogeneous? Homogeneous. Constant coefficient? Constant coefficient. What is the degree of it? It is of degree 2. So the characteristic equation will be having of degree 2. What is the characteristic equation of it? So the characteristic equation is so degree 2. So it will start from r square minus this term, this coefficient, which is 1 minus r, 1 into r minus 2 equal to 0. Right? How we basically got, maybe if you want, I may write one more line. So r square is equal to r plus 2. It is in other way, it is r square is equal to r plus 2, because after doing this calculation we got this, and now I have to take it in one side. I got that characteristic equation is equal to r square minus r minus 2 equal to 0. Now if you solve it, what you will get, because it's a quadratic equation, if you solve it, you will get, after solving, you will get r is equal to one equation is 2, another one is minus 1, right? R minus 2 into r plus 1 equal to 0. So you got two solution of it. How you can solve it? By Siddharacharya rule also you can do. Minus b plus or minus b square minus 4ac minus p plus or minus root over of b square minus 4ac by 2a. That formula will gives you this value. So we got two roots of the characteristic equation, which is 2 and minus 1. But these roots are distinct. So what is the general solution according to the previous problem, previous theorem? So the general solution is, therefore, general solution is an is equal to alpha 1 into 2 power n plus alpha 2 into minus 1 to the power n. Right? So everything is known here. What is not known? Alpha 1 and alpha 2. So we have to solve this, find out this alpha 1, alpha 2. How to get? We have some initial value. Take the help of initial value. So initial values are given as a0 equal to, now a0 equal to 2. So put n equal to 0 in the recurrence relation. What we will get? So n equal to 2 I am putting. So a0 is 2 is equal to alpha 1 into 2 to the power 0. 2 to the power 0 means 1 plus alpha 2 into minus 1 to the power 0. So this basically you will get this side alpha 2 plus alpha 1 plus alpha 2. You get alpha 1 plus alpha 2. This is equation 1. Then again initial value a1 is equal to 7, it is given. So put in the recurrent solution n equal to 1. So a1, left hand side, a1 is 7 is equal to alpha 1 into 2 to the power 1. So alpha 1 into 2 plus alpha 2 into minus 1 to the power 1. Right? So alpha 2 into minus 1 to the power 1. So this you will get 2 alpha 1 minus alpha 2. So we got two equation, right? This is alpha 1 plus alpha 2 equal to 2 and 2 alpha 1 minus alpha 2 is equal to 7. I got two equation. I can solve for it. So if you solve it, you will get alpha 1 is equal to, by elimination method you solve it, you will get alpha 1 is equal to, you will get 3, and alpha 2 is equal to, you will get at as minus 1. So these are the solution. Hence the final solution. Is an is equal to alpha 1 value is 3 into 2 power n, then minus 1 to the power n I have, but minus 1 into, so minus of minus 1 to the power n. So this is the final solution of the given recurrence relation. This is the solution of this given recurrence relation. We got a solution of it. Clear? Easy? Okay. Next, find an explicit formula for the Fibonacci number. Now what will happen for this one? Fibonacci number. It is, we all know the Fibonacci sequence is what? Fn is equal to, maybe I'll write it as capital N. Fn is equal to Fn minus 1. We discussed in the previous problem, plus Fn minus 2. So this is the recurrence relation for Fibonacci sequence. And it has some initial value also. F0 is equal to 0 and F1 is equal to 1. F1 is equal to 1. Now how to solve it? We can solve it by the previous method. Right? So what is the characteristic equation? Characteristic equation is what? So because it is of degree 2, so it will become r square then this term is coefficient is 1, so minus r. This is also 1, so minus 1 is equal to 0. This is the characteristic equation. If you solve it, you will get minus b plus or minus root over of b square minus 2a. If I do, you will get, which implies that r is equal to, you will get two value, 1 plus root 5 divided by 2, comma 1 minus root 5 divided by 2. To two equation you will get. Therefore, the general solution is fn is equal to alpha 1 into 1 plus root 5 divided by 2 whole to the power n, because two distinct root I got, plus alpha 2 into 1 minus root 5 divided by 2 whole to the power n. Now what is unknown here? Alpha 1 and alpha 2. How to get that? By putting the initial values, right? So if you put f0 equal to this 0 and f1 equal to 1, so how to get it? F0 equal to 0 imply that just putting n equal to 0. So this side I will have 0 is equal to alpha 1 into 1 plus root 5 by 2 whole to the power 0. So it is alpha 1 plus alpha 2. This is equation 1. Again, I have another initial value f1 equal to 1. This will imply that this equation I am putting n equal to 1, right? So the left hand side it is 1 is equal to alpha 1 into 1 plus root 5 by 2. Mine plus alpha 2 into 1 minus root 5 by 2. This is equation 2, right? So this two equation I can solve it. If you solve it, you can check, just do this calculation. You will get alpha 1 equal to, after solving this equation 1 and 2, will get alpha 1 is equal to 1 by root 5 and alpha 2 is equal to minus of 1 by root 5. Hence, what is the solution? Hence, therefore, Fn is equal to, this is the solution of the recurrence relation Fibonacci sequence. Fn is equal to 1 by root 5 times 1 plus root 5 by 2 whole power n minus 1 by root 5 times 1 minus root 5 by 2 whole to the power n. We got the solution. Now, if I ask what is the 1000th term of the Fibonacci sequence, just put n equal to 1000, you will get that f1000 value, right? This is how the solution works. So this problem also done. Now these are all, these two problems we discussed, both of them are of linear homogeneous recurrence relation with constant coefficient of degree 2, and we got a characteristic equation of degree 2 only, right? Now if I generalize this concept, what will happen? Like suppose I have a linear homogeneous recurrence relation of degree k, right? So what I will get? I'll get a characteristic equation of it. What is that? It is r power k, right? Characteristic equation of this one I'm talking about, minus c1 times r power k minus 1 minus c2 times r power k minus 2. Like that I'll get minus dot 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 minus ck equal to 0, right? So I'll get, this is the characteristic equation of the linear homogeneous recurrence relation of degree k. Clear? And then we have to solve it. So if I have degree 2, then two distinct root if I get, then I will get the solution according to our theorem, this theorem, right? We have already solved two problems of it. Now we will see that if it is of degree 3, or if it is more than, like the same equation, same root if you get, like now we can extend that equation. Now find the solution of the recurrence relation where this one, look at this. What is the degree of this recurrence relation? It is linear homogeneous, right? Constant coefficient of degree what? Of degree 2. What is the characteristic equation of it? Okay, characteristic equation is what? Characteristic equation of the recurrence relation is, because it is of degree 3, so it is r cube minus this 6r square minus of minus 11, so it will become plus 11r minus 6 is equal to 0, right? So this are the distinct root or not, we will have to check. Now this is of degree 3, so we can extend that theorem and we can get some solution of it. Okay, just a second. So if I solve it, what you will get? How to solve the 3-degree polynomial equation? We can do the vanishing factor method, right? How to do that? Vanishing factor method, you know, right? So find a solution of the trial and error method. Find a solution by trial and error method. So check, maybe 1 is a solution, r equal to 1 minus 5. Yes, 1 is a solution. So by taking r minus 1, you take as a factor, r minus 1. R minus 1 is a factor. This is the vanishing factor rule. Or you can divide this one by r minus 1, because r minus 1 is a factor of it. I'll do using the vanishing factor method, because 1 is a solution, so r minus 1 is a factor of it. And then I got this equation, I'm multiplying with r square. So what I'll get, r cube minus r square. But the previous term is minus 6r square. So what I have to do, minus 5r square I have to add. So to get minus 5r square, I have to do minus 5r. So it will become minus 5r square. Then 5r plus 5r, it will become plus 5r. But the term is 11r. So I have to add 6 more r. So to get 6r, I have to add 6 into r minus 1. So 6 into, then minus 6 will come. But minus 6 already done. It is our problem is solved. Now this one is r minus 1 into, I'm taking r minus 1 common. So r square minus 5r plus 6 is equal to 0. So this part we can easily calculate. This part, how to calculate? By again Siddhartha minus b plus or minus root over b square minus 4ac by 2a. If you do that, I'll get it as r minus 1 into r minus 2 and r minus 3 is equal to 0. So I got r is equal to 1, 2, and 3. Three different equation, right? And then I got three distinct root of the equation. So I can apply the previous thing. So what is the general solution of it? General solution will become alpha n is equal to alpha 1 into r1 power n. So 1 to the power n plus alpha 2 into 2 to the power n plus alpha 3 into 3 to the power n. This is the general solution. What is unknown here? Alpha 1, alpha 2, and alpha 3 are unknown. How to get that? Put by use, substitute the initial value, you'll get that, right? So I have the solution here already. I'll show you. So this one is our general solution, alpha 1 r 1 to the power n, alpha 2 2 to the power n, alpha 3 3 to the power n. So you got, this is the solution, where alpha 1, alpha 2, alpha 3 are unknown. But now we know that initial value, put n equal to 0, n equal to 1, and n equal to 2. You got this equation. So you have to solve this three equation. You will get the alpha 1, alpha 2, alpha 3, the some value. Alpha 1 is 1, alpha 2 is minus 1, alpha 2, 3 equal to 2. So hence the final solution is n equal to 1 minus 2 power n plus 2 into 3 power n. Our problem is done, right? So practice this kind of problem. It is the extension of the previous theorem. So if you have two roots, it is alpha 1 plus alpha 2. If you have three distinct roots, alpha 1, alpha 2, alpha 3. If you have four roots, alpha 1, four distinct roots, alpha 1, alpha 2, alpha 3, alpha 4. Four different things we'll have, right? Now, like we may have repeated root also, right? We may have repeated root also in the characteristic equation. So in general, if I have again 2-degree equation, I'm talking about C1 a n minus 1 plus C2 a n minus 2. What is the characteristic equation of it? Characteristic equation is r square minus C1r minus C2 equal to 0. And if you get that the roots of this equation is both of them are same, r0 and r0, then what will be the solution? According to this theorem, if I have repeated root, the general solution will become n equal to alpha 1 r naught power n plus alpha 2 into one extra n will be added. Alpha 2 into n into r naught power n, right? If they are distinct, this n was not there, but if they are, you got a same root, you will get alpha 2 into n into r naught power n. So one extra n terms is added. Now if this equation is of degree 3, then you will get 3 same root. If you get, then it will become alpha 3 into n square into r naught power n. Alpha 3 into n square into r naught power n, right? This is how it will be added, correct? So this is not there now for the time being, so this is not required. But if I have keep on adding that, like 3 equal root, it is alpha 2 into n into r square plus alpha 3 into n square into r naught power n. This is how it will work. Now, if that is the case, look at this problem and how to solve it. So what is the characteristic equation of this given recurrence relation? It is r square minus 6r plus 9 equal to 0. And if it is basically r minus 3 whole square, right? So r is equal to 3 comma 3. So the equal root I got, right? Equal root for this equation. So what is the solution? The general solution is an is equal to alpha 1 into 3 power n plus alpha 2 into n into 3 power n. This is the solution of it. What is unknown here? Alpha 1 and alpha 2. How to get that? By taking the initial value. Put a1 equal to 0. So a1 equal to a0 equal to 0 imply that a0 equal to 1 imply that 1 is equal to alpha 1 plus this part is 0, so plus 0. Basically alpha 1 is equal to 1. I got it. Again I have a1 equal to 6. This will imply that 6 is equal to alpha 1 into 3 to the power 1. So 3 alpha 1 plus 3 to the power 1 into 1. So plus alpha 2. Right. But alpha 1 equal to 1 we already got. Therefore alpha 2 is equal to 6 minus 3 alpha 1. So 6 minus 3, it is 3. So alpha 1 is equal to 1, alpha 2 equal to 3. Hence the final solution is n equal to 3 power n plus 3n into 3 power n. This is the general solution of it. We are done. Correct. Now if I have more than two number of equal root, what will happen in that case? Look at this problem. So extension of this previous theorem. So this is the 3-degree recurrence relation, right? It is a 3-degree recurrence relation. And what will happen in this case? What is the characteristic equation? It is the characteristic equation is, so 3 degrees, so r cube, then minus 3, so it will become plus 3r square, then this one also plus 3r plus 1 equal to 0. Now what is the solution? It is actually basically r plus 1 whole cube formula, it equal to 0. So r is equal to -1, -1 and -1. So all three roots are repeated. So how to get the solution, general solution? So we have already discussed, because three roots are there, so general solution will become an is equal to alpha 1 into -1 to the power n plus alpha 2 into n into -1 to the power n plus alpha 3 into n squared into -1 to the power n. This is the general solution. And after that, how to get this alpha 1, alpha 2, alpha 3? By substituting this value, right? So if you substitute this value, I am not going to do that. It is already there in the solution. If you substitute these three values, you will get as this thing. So this one is the, if you substitute the value, you will get three equation with three unknown. And then if you solve it, you will get alpha 1 is equal to, you do it in your copy, you will get alpha 1 equal to 1. You will get alpha 2 is equal to alpha 2 is equal to 3, and you will get alpha 3 equal to -2, right, after solving these three equations. And then final solution is this one. Now we have discussed that if I have distinct root of the characteristic equation, how to solve it. We have discussed if we have that equal root, how to get the solution. Now if we have mixed kind of a root, how to get the solution? Mixed kind of root means, suppose in a 3-degree equation I have two roots are same, one root is different. If I have in a 3-degree equation, characteristic equation, two roots are same. So suppose the characteristic root r is equal to two roots are same and the another one is different. Then what is the solution? In this case, an is equal to, the first two will be, because we already know that if two roots are same, what is the solution? It will become alpha 1 into r naught power n plus alpha 2 into n into r naught power n. This is the first part, and distinct root r1 plus just alpha 3 into r1 power n. This will be the solution, right? Now then accordingly all these things work. Now I may also have that maybe r is equal to roots are r0, r0, r1, r1. What will happen? So for these two, the equal roots case, whatever is the formula, that will work. And for these two, again for the equal root, whatever is the formula, that will work. So you'll get a general solution in this way. And after that, just putting the initial value, you'll get the final solution of it. I hope this is clear. So if everything is understood, the last problem for this lecture, it is this one. Suppose that the roots of the characteristic equation of a linear homogeneous recurrence relations are that 2, 2, 2, then 5, 5, 2, 2, 2, the roots of the characteristic 2, 2, 2, 5, 5, and 9. That means 2 is coming 3 times, 5 is appearing 2 times, and 9 is single. What is the form of the general solution? This is how we discuss. So basically, the characteristic roots are 2, comma 2, comma 2, then 5, comma 5, and then 9. What will be the general solution? General solution an is equal to, because of these things, we know the formula, we'll apply that. Alpha 1, 2 power n, plus alpha 2 into n into 2 power n, plus alpha 3 into n square into 2 power n. This set is done. Then I have two repeated root for 5. For that, I know the formula. So I'll have alpha 4 into 5 power n plus alpha 5 into n into 5 power n. Plus, I have this distinct root. So it will become alpha 6 into 9 to the power n. So this is the general form of it. Right? So we are done with this. So we know that if it is roots are distinct, what is the formula? We know if the roots are like repeated, what is the formula? And if both the situations are there, how it will work. Right? So I'm done with this lecture. So this is how these things will be there. All the content I have taken from the book of this Kenneth Rosen book, Discrete Mathematics and its Applications. So today's lecture I went little fast, but I hope you understand. So you have to practice in your copy, right? Finish all the solution. I just keep the solution. I just explain to you how it works. If the videos are helpful, you can share with your friends. You can press the like button and please subscribe to this channel. I think this channel is helpful for you because there are another set of lectures that you need it in future as well. Thank you very much. I'll come up with a new video in the next lecture. Bye-bye.